Okay, guys, as I promised, I was gonna walk you through a code I wrote to demonstrate the analytical solutions to the Poschel-Teller potential. The solutions obtained if we expand the unknown wave function into harmonic oscillator basis, and the solutions obtained if we use physics-informed neural networks, okay? So I will have a link to the GitHub to this code so you can use it. A few thoughts before we start talking about this. I did this on Google Colab because everybody has access to it, and I will provide the link so you can use the code. I have the paid version because I like playing around with machine learning projects, but I believe the free version will work fine with this code. What else? In case you want this to be like an academic project or a publication quality project, I think Python won't cut it. You will probably have to do some of the calculations with C++. I mean, C++ is the best language, I guess, one of the best languages, along with Fortran, to do scientific calculations with high accuracy and fast, because there are many routines and libraries that do numerical integration and stuff that you need to do these things. So anyway, let's start. I will go cell by cell and just describe what I did, and hopefully this is useful. So here we just import various libraries we will need. NumPy is needed to create arrays and such. Matplotlib is used for plotting. Pandas is used to cast arrays into nice tables that you can that make your data more visual. Then from SciPy I use Eigen that does matrix diagonalization. Simpson from Integrate that does Simpson integration. Okay, and some of the special polynomials that we need and special functions are imported also from SciPy. And then Torch is PyTorch. That's used later when we discuss neural networks. Okay, so in the first part, we will just see a few things related to the analytic Poschel-Teller solutions. So here we define the constant for the potential. Remember that the potential is 1/2 lambda times lambda plus 1, which is exactly what we wrote here. And we set lambda equal to 8, okay? And I wrote there that lambda has to be an integer larger than or equal to 1, okay? So this is the V Poschel-Teller. This is what the notation means. So it returns minus V naught, which is minus lambda times lambda plus 1 over 2 times the hyperbolic second. And because the hyperbolic second is not implemented, we use 1 over the hyperbolic cosh, which is equivalent to the second squared, okay? Oops, I messed the code. Here we define the eigenvalues, which are simply minus mu squared over 2, okay? And this is the analytic normalized eigenfunctions that we worked in the first video. So this is the normalization factor, and L, P, M, V are the, if you hover over this, it shows you what this stands for. So you see, it says, associated Legendre function of integer order and real degree. And if you scroll down, it tells you what to do. So the arguments that the function takes, etc. So this is a function imported by SciPy, pretty much, okay? Okay, I hope this makes sense. And here we plot, oops, we didn't execute the cell, you see, okay, sorry. So here we see a plot of the potential. And again, we set lambda equal to 8. So this is what the potential looks like, okay, with the black color. And then with gray, we get the ground state wave function that has mu equal to 8. okay? For mu equal to 7, we get the first excited, second excited with mu equal to 6, 5, 4, 3, 2, 1, okay? So these are all the bound states. And you see that the most highest excited state with the blue there is almost like, it looks almost like a wave because it's barely bound, okay? So it starts looking more like a plane wave than a bound state, if that makes sense, okay? And with the dashed lines, we plot the eigenvalues corresponding to the eigenfunction that we plot, okay? So for example, since lambda is 8, the lowest bound state, which is the ground state, has an energy of minus 32, which we see here, okay? And here is the ground state wave function that looks like a Gaussian pretty much, okay? I hope this makes sense. Now, one of the things we can do is to integrate and check whether these wave functions are orthonormal, because this is something we promised. And this is what we do here. I define a grid, and this is how a grid is defined. So this divides the interval between minus 100 and 100 into 200,000 points, okay? And we define the overlap matrix to be a matrix of dimensions 8 by 8, right? Yes. Okay, 8 by 8 is the overlap matrix. We initialize as zeros and then we populate that matrix with the overlap integrals, okay? So what we do here is pretty much this. We find this overlap, lambda. Okay, let me comment this because it's not code, okay. So we calculate these overlaps, which are integrals from minus infinity to infinity of these wave functions over here, okay? These wave functions, okay? And to calculate that integral, we use, okay, we use two wave functions pretty much, psi1 and psi2, psi1 and psi2, and then we do a Simpson integration in that grid, okay? Remember, this should be from minus infinity to infinity, but this is numerical integration. Minus 100 is good enough because at minus 100 the wave function is pretty much zero, okay? So we do that. Let's execute, and it takes some time. And here is our matrix, which is diagonal as expected. So you see, so our wave functions are indeed orthonormal because all the overlaps are zero except the ones on the main diagonal that have the same lambda and mu. Okay, that's good news. Okay, in this next cell, we will do something that we haven't done when we discussed about diagonalization and such in the notes, which is to verify that the Hamiltonian matrix is in the analytic basis is diagonal, which means that, remember that this is the Hamiltonian pretty much, right? So if we focus on the right-hand side, okay, if we obtain the natural solutions to the problem, which are the Legendre polynomials, as we saw, these ones, okay, the ones we plotted here, then if we take this inner product n and then e and then m, okay, we will pretty much, this is the constant gets outside the integration. So what I'm trying to say is that the Hamiltonian matrix should be diagonal just like this matrix, okay? And this only happens in the original basis in the natural basis of the problem, which is the Legendre polynomial solutions, okay? In the harmonic oscillator basis, as we will see, the Hamiltonian matrix is not expected and will not be, is not expected to be diagonal, and it will not be diagonal, as we will see, okay? So to do that, though, we will actually integrate the Poiseuille-Teller wave functions just to make sure that everything works. So we define an interval dx, which is just x grid, which we used earlier, okay? So X grid. So this dx is going to be pretty much 1 over 200,000, right? Because we're taking 200,000 points. So we take this dx for taking the numerical derivative of the wave functions that we need, okay? We initialize the Hamiltonian matrix here as zeros, and then we do this loop here to calculate, okay, first we need psi1 and then psi2, okay? Both of them evaluated at this grid, and then this function over here, sorry, this variable over here, psi2 ddx, is the second derivative of psi2 pretty much, which we calculate using an NumPy method called NP gradient, okay, which takes the function that we want to differentiate, an interval dx, which we define there, and then it does this twice, okay? And then the integrand is going to be psi1 from here times minus 1/2 from the operator of the kinetic energy times the second derivative plus the potential evaluated at the grid points times psi times psi2. Okay, and for the integration we use the Simpson method like before, and this is the Hamiltonian matrix. These are the Hamiltonian matrix elements. Okay, and here is when I use pandas so that we get a nice representation of this matrix. Okay, so I hope this makes sense. Let's evaluate this. Okay, let's evaluate, and this is the matrix. Okay, you see that it's diagonal. We get some artifacts like these ones. This has to do with the fact that we are actually performing numerical integration from minus 100 to 100, so it's not exact, just as if we are using minus infinity to infinity. And we have rounding errors and such, but this is good enough. And notice that these are the eigenvalues, guys. Remember that the energy, if lambda is equal to 8, the ground state energy is going to be minus 32, because that's minus 8 squared over 2. Then the first excited is going to be minus 7 squared, which is 49 over 2. So it's going to be minus 24.5, minus 18, minus 12. So these are the eigenvalues, okay? And this is what happens when you're dealing with the native basis, okay? So this pretty much summarizes the exact solution. So this is the companion to the first video we did where we derived the exact solution, okay? Now let's go to part 2. How can we obtain this spectrum and the wave functions using a harmonic oscillator basis expansion, okay? So here we define various things we will need. We define h bar, m, and omega, and we set them equal to 1. We define the harmonic oscillator potential. We define the harmonic oscillator basis using these Hermite functions and the normalization. We define this dimensionless quantity xi, though we don't have to, because in our case, xi and x are the same as we take omega and h bar and m to be 1. These are the eigenvalues. And like we did with the Poschel-Teller potential, let's plot. Again, I forgot to initialize this cell, sorry. So let's plot. So this is the ground state wave function, the first excited with orange, with green we get the second excited, and so on. Let me show you what omega does. So if we increase omega, what do you expect to happen? Write in the comments. So let's do it, let's make it 2, okay? And now let's see. The wave functions get a larger lambda, pretty much, okay? Let's decrease it. Let's do it let's make it 0.2. Now let's see. Okay, we get an even, sorry, now we get a larger lambda. Earlier we got a smaller lambda, okay? But anyway, let's keep it to 1 and keep moving. You can play with the notebook at your homes. And by the way, you don't need Google Colab to work with this notebook. You can open it with Anaconda in your environment. In case you don't have all the libraries listed over here installed, you can install them in a virtual environment, etc. You can ask me in the comments and I can provide answers if you run into trouble, but it's kind of straightforward, okay? Okay, where were we? Over here, okay. So these are our basis functions, the first 8 at least, okay? Because we can use many more, as we will see. Here we do the same as we did before. We verify the orthonormality of the harmonic oscillator basis. We use a new grid and we go up to 8 and we define this matrix, and let's evaluate this. It's the same procedure as before. We use the Simpson method for integration and so on. Okay, so we see that we get a diagonal matrix pretty much. Okay, so that's good. Now comes the magical part. Okay, we will calculate the Poiseuille-Teller Hamiltonian matrix in the harmonic oscillator basis. Okay, we use 150 basis states to get better convergence, but even 50 will work. We will test it later. Okay, we use a new grid again. We define a dx because we need it for taking the gradient. Okay, and we initialize the Hamiltonian matrix, and we use the harmonic oscillator basis now. Okay, so psi n and psi m. We calculate the gradient again, though we don't have to do that. Remember in the notes I told you that there are special functions, special formulas, at least for the kinetic energy representation matrix, for the kinetic energy operator representation in the harmonic oscillator basis. But anyway, we will not do it like that. So the integrand is going to be psi n times the second derivative of psi m times the Poiseuille-Teller potential times psi m, okay? And we use the Simpson method. We cast this Hamiltonian into a pandas data frame for better visualization, and the calculation was performed, and you see the results here. So the Hamiltonian matrix is now not diagonal, okay? So this is the Hamiltonian matrix of the same problem, pretty much, the Poiseuille-Teller potential, but now in the harmonic oscillator basis, okay? So we have diagonal elements as expected, but we also have off-diagonal elements, if you can see, okay? And same here, 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 and so on, okay? You can study this at your own time. But for now, we can just diagonalize this matrix and get the eigenfunctions and the eigenvalues, okay? And we do that using this library called EIG. EIG-H, it's a SciPy method, okay? Solve a standard or generalized eigenvalue problem for a complex Hermitian or real symmetric matrix, okay? So you can read about it and play with this method. But anyway, we just pass it the Hamiltonian in the harmonic oscillator basis and list the first few eigenvalues from the harmonic oscillator basis diagonalization, and we plot the function. So let's evaluate this, and you see that numerically we get the ground state as minus 32.00 whatever, whereas the analytic is this. The first excited is that, numerically and analytically it's that. So we get a really good agreement pretty much, okay? And I also calculate the error here. So the error is at most 0.01, which is really good, okay? And here we plot the numerical harmonic oscillator basis for the ground state and the analytic Poiseuille-Teller wave function for the ground state. Mu equals 8 is the ground state, okay? And we also get the first state, and we plot it along with the analytic solution, and we see that they overlap. This is crazy. It's really good, okay? So let's see what happens. Let's do one more test. Let's do 15 basis states, okay? Do you think it's gonna be as good? Let's see, okay. Okay, with 15 basis states, you see that the numerical harmonic oscillator basis is not exactly the same as the analytic one, okay? So we need more basis states to capture the ground state, if that makes sense, okay? One more thing you can test is to change, okay, let's go back to, let's do 50, okay? It's gonna take some time again, okay? Diagonalize, and the agreement is perfect again, okay? Let's change omega and see what happens. So omega was defined all the way up here. So let's make it 10, okay? Let's go calculate the matrix again with 50 states, 50 basis states, and let's see. Okay, the agreement is actually perfect again, but you can play with changing how many states you keep and the value of omega. You can play around and see how things change. It's a good exercise. It will teach you a lot about basis expansions and such, okay? All right, I'm gonna move on. So I guess all the money are in this part, the physics-informed neural network solution, okay? This got me really excited because this was something I tried for the first time in my life. I wasn't even aware that this was possible, to be honest, up to a few weeks ago. So that's kind of crazy. So in this cell, we define the width and depth of our neural network, pretty much, okay? We also define how many training points we will get. So from the video about the PINNs, these are the actual data points that we get from the wave function itself, okay? And we also use a range of data points. So from this range of data points, we will get 40 points. Now for the physics points, we will get 800 points in the range -8 to 8, okay? The learning rate, the number of epochs are related to the neural network we use that has a width of 50 and a depth of 6, okay? Depth means the number of layers, and width means the input, how many inputs it can take, pretty much. The initial guess is that for the energy, we take the weight of the loss function related to data is 1 and the weight of the loss function related to physics as 2. And these two parameters are related to the network, okay? So we initialize this configuration. So we get all these parameters. And the device used is going to be a CPU. We can use CUDA, but for this demonstration, I'm using a CPU. Okay. In this cell, we prepare the training data from the analytic ground state. And we also initialize the physics points and plot what we do, okay? So the analytic ground state is shown there in black. The red dots are the data points, the actual data points that lie actually on the wave function itself. And the blue dots are the physics points that we will use to solve the Schrodinger equation, pretty much, okay? Okay, I hope this makes sense. This is the network itself. So we use linear layers with hyperbolic tangent activation, and we do forward passes. What else? Here is where we add the layers, and this is where the width and depth come into play that we define in the configuration. So that's the width and that's the depth, and we convert the initial guess of the energy into a tensor, so we can use it with this configuration. We define the Poiseuille-Teller potential as a torch function, so we can use it when we perform calculations. Here we define the Schrodinger residual, so we cannot use the gradient that we used before from NumPy. We have to we pretty much, when you use PyTorch, we have to use all the functions defined by PyTorch, because everything has to be a tensor. Okay, this is something related to PyTorch. So this is the wave function. Okay, and this is the second derivative, where we take autograd pretty much to calculate the second. Okay, so this is the, this is the wave function, and the wave function is nothing but the neural network model pretty much. Okay, then the first derivative, for the first derivative we use autograd, and for the second derivative we use autograd on the first derivative. Okay, and this is our potential, and this is the residual, 1/2 times the second derivative plus Vx minus E tensor, and E tensor was defined here, okay, times psi. Okay, in this cell we have the training set up. So these are all the parameters that we need to optimize, which are the parameters of the model itself, and the model is this one, the PINN model that we defined up here. The optimizer is an Adam optimizer, okay, and the learning rate is taken from the configuration that we define. The scheduler is an LR scheduler with an exponential LR, and this gamma that we take from the configuration. And this is the training loop, okay? So for all the epochs that we defined, we start with optimizer 0 grad. This is standard stuff that you can learn in another video. So this is where we calculate the, okay, this is the loss related to the data that we talked about in the video, and this is the loss related to the physics, okay? So this is the residual from the Schrodinger equation, okay? So we pass the physics points, the model, the potential, and the guess for the energy. This is the combined loss, and then we have to do a backward propagation and take a step. And here, okay, we stop at the scheduled epoch, and we print every 1000 epochs, okay? I hope all this makes sense. So you press start, and the model is not defined because we haven't initialized this cell, okay? So let's go back to this, and it will start training. I will probably edit this part out until it runs. So, okay, for the 0th epoch, for example, the total loss is 0.63, and this comes from the data and the physics. Remember that we weighed the physics loss twice, so 2 times 0.27 plus 0.09 gives you that pretty much, okay? So the initial guess is minus 30. Remember that we have to find about minus 32, okay? If we go to epoch 1000, the loss drops significantly, and the physics loss improves significantly. And anyway, okay, the training is done. As you can see, the final, this is not the final, this is epoch 9000, but okay, we trained for 10,000 epochs, so 10,000 iterations pretty much. Okay, the total loss is 0.001, and the loss that comes from the data is really small, and the same goes for the physics loss, and the energy converges to what we are expecting, to minus 32, which is crazy. So in this cell, we plot the ground state wave function as we calculated it analytically and compare with the neural network, and we get an exact match, okay? And as far as the energy goes, we have an error of less than 0.01, which is crazy. So this is a good, really good approximation, okay? So I hope this is useful. As I said, I will create a link to this code on GitHub, and I will be really happy to expand this if people want, and I will be happy to explain how it works if you run into trouble. But anyway, I thought that this was a good exercise in quantum mechanics, and a good exercise in a very modern approach that you can use to calculate wave functions, which I find amazing, to be honest, okay? I hope you enjoyed this video. Let me know if it's useful. See you in the next one.